All right, hey everyone. I'm Tim Woodard. I'm a principal solutions architect at Nvidia, where I focus on professional visualization, so mostly in the public sector. So think of that as people in government that want to put a pixel on the screen. I'm your guy if you need help with that. My background, I spent 20 years building visual systems for flight simulators. And this is, of course, a big geospatial problem. We're taking all kinds of geospatial data sources and constructing a 3D environment. And the goal is to create a realistic environment to train humans to perform, difficult or critical tasks. Really kind of fun job. And so my role at Nvidia is kind of supporting this industry for everybody that's doing this. And all of these guys need geospatial processing. And one of the big challenges we see is the time that it takes to process this data and prepare it for visualization or analytics. So what's NVIDIA's role in geospatial processing? To maybe step back and describe what NVIDIA does, of course you all know NVIDIA makes GPUs, right? Graphics processing units. We also make CPUs and DPUs, data processing units, NICs, and then computers that use those components to build specific computing architectures that address particular problems, optimized architectures that remove bottlenecks for things like AI or visualization. What most people maybe don't realize is that most of the people at NVIDIA are software engineers. And there we focus on building libraries that accelerate common algorithms that utilize a GPU, that can leverage the parallelization of a GPU, which is why you've seen this kind of a end to Moore's law, right? And this is kind of an old idea by now, but if you haven't heard it, it used to be that about every 10 years, you could expect a 100x improvement in performance in an algorithm running on a CPU. With GPUs, because of the parallelization that you can leverage with thousands and thousands of cores, it's closer to like a million X in 10 years, and sometimes faster than that. So, if you hadn't seen it, this is a video from 2008 where the Mythbusters explain the difference between a CPU and a GPU. Oh.
And he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1. Let me speed it up.
It's overclocking it.
Ladies and gentlemen, Leonardo. Trigger on this thing. 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes, in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
In 10,
9, 8,
7, 6, 5, 4, 3, 2, 1.
Ladies and gentlemen, science class is now over.
All right, so whose was the first time seeing this video? Any of you? All right, cool. Glad you got to see this. I was in the front row for that, and you could feel the shockwave when that thing blasted off. It was pretty awesome. So obviously, GPUs are great at computer graphics, and that's because computer graphics is what we would call embarrassingly parallel. It's very easy to divide up the workload and take advantage of all those cores. But it turns out there's a whole class of algorithms in general purpose computing where we can take advantage of this as well. And so this is where CUDA comes in. You all know about CUDA? Anybody? CUDA? So CUDA is our programming language that allows you to, with C-like language, take advantage of the GPU. And the idea here is not that your whole application runs on the GPU. You still utilize a CPU to orchestrate all of the commands, but you find those hotspots, those parts of your code that take up a large percentage of the time, and it's usually a small amount of the code. Things where you have double nested loops, right? And this comes up all the time in geospatial, where you're processing pixels in an image, for example. And so you take that part of the algorithm and you offload it onto the GPU, and you get this massive speed up. That's the idea with CUDA. But it's not necessary that you go all the way to the lowest level and write CUDA code. In fact, we have a bunch of libraries that we built on top of CUDA that leverage the GPU for you, and you just have to drop in those libraries into your application and make a few function calls to take advantage of that. So there's CUDA-X libraries for every domain. If it's a thing that can be accelerated on the GPU, we probably have a library for it. A couple that are interesting up here that relate to geospatial, cuOpt. So if you look up cuOpt, that does optimized route planning. So like the traveling salesman or pizza delivery problem. What's the most efficient route if you have multiple destinations along the way? It's great for logistics and warehouse planning, large-scale route planning. But a few that are maybe a little bit more specific to geospatial, I'll draw your attention to. One is Spatial. So if you use GeoPandas in your code, this is basically a compatible library that allows you to do vector and point processing. And in this case, you can achieve thousands of times more points processed per millisecond by offloading that work onto the GPU. And it has things like trajectory, polygon, and line string bounding box support. You can ask as a point inside a polygon and compute nearest neighbor, all these kind of things really, really fast. What about image processing? Well, we have Nvidia libraries that are CUDA accelerated for dealing with TIFFs, including GeoTIFFs. I'll draw your attention to a little code sample here that shows how you can encode a GeoTIFF, and there's support for all the GeoTIFF metadata that would be necessary to create an image. And then under the hood, you can compress that using various payloads like NVJPEG or JPEG 2000, which are also CUDA accelerated. And speaking of JPEG 2000, you can do things like if you have a massive JPEG 2000 image, you can decode an area of interest, so you don't have to decode the entire image. And you can decode to a target resolution. So this is really great if you're trying to generate LODs for terrain. Who knows about, who here's done anything with ray tracing before? Familiar with ray tracing? So if you're not, rasterization is the way we normally do computer graphics, where you take polygons and you project them into screen space, and then convert those polygons into pixels one at a time and compute a color. Ray tracing is kind of the opposite. You start with a pixel and you cast an imaginary ray into the virtual world and ask the question, what was hit? And then based on that hit point, you cast other rays and calculate how light travels back to that pixel, compute a final color. Awesome for computer graphics, but there are other applications. So as it turns out, orthorectification is a ray tracing problem. And so we did a sample of building an orthorectification pipeline that could take imagery from a sensor and do real-time faster than real-time orthorectification using the GPU and ray tracing. In this case, it was about 700 times faster than trying to do it on the CPU. So you could be taking data off the collection platform and orthorectifying on the fly. Really pretty incredible. And that's basically just taking every pixel in the ortho image, casting a ray to the virtual terrain, and then at the hit point, you go to the sensor plane and do a texture lookup. Really pretty simple algorithm. Very elegant, very, very fast. And you can also tell which points would be in shadow, which might be useful if you care what parts of the image are actually correct. Another example of using ray tracing would be sensor and signal processing in a geospatial context. So telcos use ray tracing with a large-scale geospatial model to analyze how 5G signals would propagate and interact with various surfaces. So the idea here is we use Omniverse. In this case, Ericsson built a city-scale digital twin in USD, and then they use optics, that same library that I just talked about for orthorectification, to determine like how signals would travel from a virtual antenna to a van that's driving around. And they can measure beam signal strength and forming, all those kind of things. Next on the list is fVDB. So fVDB, deep learning framework for spatial processing. We use this for a lot of different things, one of which being 3D reconstruction. So you've heard a lot about Gaussian splats this week. We can accelerate Gaussian splats using this platform by significant amounts. So imagine normally something taking on the order of days to train a splat and then maybe extract a mesh. We're down to minutes and sometimes seconds for some of these processes. And we can do this at a large scale. So as a quick example of how we've applied this, me and a colleague and another colleague flew a consumer drone around an area in Atlanta called Safety Park, just did a 360 turn and ran that through a feature extraction process, ColMap. Some of you may be familiar with that. And then we trained a NERF. So if this could be Gaussian splats or NERFs, it doesn't really matter, but in this case we trained a NERF. It's super fast using Neural Angelo to then extract a mesh. And so from that NERF we can take this mesh and GPU accelerate the processing of this. So one of the things we want to do is take vertex colors and convert it to texture, because that's like a 20 million polygon mesh. So we parameterize it in 2D space, create the texture, and then we can decimate the mesh. Now it's useful for things like 3D visualization. So we take that mesh and then we convert it into 3D tiles. And then you can bring that into all kinds of applications like Unity, Unreal, or Omniverse in this case. And so this was an accelerated pipeline using GPU processing at every step. And that allows us to go much quicker than traditional photogrammetry. Above ground is cool, but so is below the surface of the water. So MITRE is using fVDB to do underwater processing. In this case, they take the underwater bathymetric information, and they can simulate how sensors operate in that environment, like sonar. And so this is a really interesting kind of ray tracing spatial problem as well, and visualize the output of those returns back in a geospatial context. They also do route planning. So this is kind of back to that CUOPT example, where what's the best path that I can take through a series of obstacles. And then they also simulate the underwater volume. So things like the salinity and temperature of the water affect the buoyancy of that craft. And so being able to represent that in fVDB allows them to accelerate the processing of those things. But what about AI? AI is what I like to call the universal function approximator. If you have enough examples of input and output, you can train an AI to do just about anything. And we could go on and on about examples, but there are some geospatial ones that I think are worthy of mentioning. We have an effort at Nvidia called Earth-2, where our goal is to do climate simulation at a global scale, but at sub-kilometer level. So that's a very difficult challenge, and normally you need HPC cluster that would take a weekend to go run one of these models. We're building proxy models that use AI as a surrogate for those HPC codes, and that allows us to do global scale simulation, again at a sub-kilometer scale, which is really quite incredible. And this is also in conjunction with 3D tiles and cesium, so being able to do things in an urban environment. So how is wind and weather going to be affected by the buildings and terrain in an area? This is something that weather prediction today hasn't really been able to achieve, but by being able to speed up and simulate these processes using AI combined with geospatial data allows us to potentially make much better predictions about what's going to happen in the future. The last thing I'll mention is Cosmos. So we have these world foundation models that we're building that have been trained on millions and millions of hours of video out in the real world. So in this example, we're taking images that are rendered perhaps using very simple kind of geometry and color, and then transforming those videos and images into photorealistic output. And so this goes back to that first example I showed where, of a flight simulator. One of the things that we're trying to do at NVIDIA is enable autonomous systems development. These are going to be systems that operate in the real world, and they need lots of examples of what the real world looks like and how it behaves. And so these world foundation models are able to take computer graphics that are very easy to produce using Unity, Unreal, Omniverse, etc., and produce then photorealistic video that can train those AIs because we have all the semantic labels. It's the perfect training data set. And here you can see, given a text prompt and that input video, we can create all different kind of variations of output, different weather conditions, different lighting conditions. This would be very, very difficult to go collect in the real world. And someday, when you're going to have a robot in your kitchen, it could be all these different kinds of kitchens. Who knows? Smaller scale geospatial, I suppose. So with that, I have time for a few questions. What do you got? Good.